SciShow Space is supported by Brilliant.org. It seems like something cool is always happening with Tabbys Star. Back in May, we got all excited because it was dimming again, and even though we haven't found anything out from that yet, the star is back in the news again. According to a paper published last week in the Astrophysical Journal, astronomers might have finally discovered part of why the star acts so strangely. And I know what you're hoping, but it's still probably not an alien megastructure. Those chances are dimming even more than the star is. Tabbys Star, lesser known as KIC 8462852, is about 1,300 light years away. It's nicknamed after Tabitha Boyajian, who was the lead author on the first paper about it. Since its discovery, it's been one big mystery. We've not only seen it continually dim over long periods of time, but we also keep seeing short, randomly timed dips in brightness. It's not like anything we found in stars similar to what Tabby is supposed to be. To explain this data, people have suggested everything from broken up comets to a massive structure built by extraterrestrials. Now, in this paper, astronomers are shedding a little more light on the situation, and they did it by collecting light, specifically more types of light. Using NASA's Spitzer and Swift telescopes and the Astrolab Iris Public Observatory in Belgium, astronomers intermittently monitored 3 types of light coming from Tabbys Star between September 2015 and December 2016. Those are infrared, visible, and ultraviolet light. They found that the infrared light dimmed less than both the visible and ultraviolet light, or in other words, that the dimming depended on the wavelength, and that gave them some clues about what could be happening. They concluded that this difference could be from an unevenly distributed dust cloud orbiting Tabbys Star about once every 700 days. Each particle in the cloud wouldn't be more than a few micrometers across, because anything larger, like a megastructure, would block all wavelengths equally. The idea is actually similar to how sunsets get their red hues. Shorter wavelengths of light, like blue and ultraviolet, collide with tiny particles in the atmosphere and get scattered more than longer wavelengths, like red and infrared. So at sunset, when the sun is lower in the sky and the sunlight has to travel through more of the atmosphere, it's the redder light that makes it into your eyeballs. On the other hand, when the particles in the atmosphere are too big, like with small raindrops in clouds, all the wavelengths get blocked equally and you get gray skies. Now, this proposed dust cloud could explain the long-term dimming, but not everything. Like, it doesn't address the short extreme dips in brightness we've seen, which previous studies have suggested might be caused by comets. It also can't explain 2 brightening events, one in 2006 and one in 2014, that another team of astronomers may have found. That paper hasn't been peer-reviewed yet, so we can't say anything for sure, but it could throw a wrench into the works because astronomers have assumed Tabbys Star was only dimming. So we might be getting close to an answer, but Tabbys Star remains a mystery for at least a little while longer. But speaking of astronomical mysteries, astronomers may have discovered what triggers a Type 1a supernova. According to research published last week in the journal Nature, they could be caused by a helium nuclear explosion, which is as intense as it sounds. Some supernovas happen when supermassive stars collapse, but a Type 1a supernova happens when a white dwarf, the remnant of an old star, gets too massive and explodes. Usually this happens because it's been siphoning off matter from a companion star in a binary system. Type 1a supernovas are a really important tool in astronomy. No matter where in the universe they are, the light they emit evolves following the same pattern. That means it's relatively easy to calculate how far away they and their galaxies are. And studying them was actually how we found out the universe's expansion was accelerating. But we did all that without actually knowing what causes white dwarfs to go boom. And now we might have solved that mystery. Using the Subaru Telescope in Hawaii, an international team of astronomers scanned a large piece of the sky looking for baby supernovas, only a few days old. In each galaxy, Type 1a supernovas only happen about once per century, so they used a wide field camera mounted on the telescope to try and capture as many as possible. And they found a bunch of them. One candidate, about 1.5 billion light years away, officially called SN 2016 JHR, appeared to be only about half a day old. That is super young, younger than any previously studied supernovas like it. It's so young that the light it emitted didn't even match what astronomers usually find. After tracking this object's light curve for 2 months, the team used a supercomputer to try to model their observations. According to the simulations, the star collected enough mass from its companion star that a thin shell of helium on its surface experienced extreme temperature and pressure. It was enough to fuse the helium atoms and create an explosion. The resulting shockwave then traveled down into the white dwarf, causing the carbon inside the star to ignite. And that created the energy needed to rip the star apart in an explosion 5 billion times brighter than our sun. Understanding how these explosions are triggered and what they look like just hours after starting will be important, because it'll help astronomers improve those distance measurements and how we understand our universe's history. Speaking of stars, most of us know that our sun is kind of your average Joe, unlike tiny white dwarfs or huge red giants, which is pretty common knowledge now. But what about way back in Greece around 200 BCE? Our partner Brilliant.org has a cool lesson about how Greek astronomer Aristarchus tried to estimate the size of the sun. And I'm going to look through it.
Brilliant's really cool because it gives you context. Like, instead of just giving you this math problem, it's putting you in the headspace of an early astronomer. Each little quiz is building on the previous one, so you're applying what you learned in the last section to this new section. It's fun because it's kind of like a game and I want to win, but more than that, I really just want to know the answer and learn more about it. So when you get a question wrong, you're still learning a cool thing. Thanks for pretending to be Aristarchus with me and checking out Brilliant.org. If you want to support SciShow Space and test your knowledge and try this out for yourself, you should click on the link in the description and check it out.
The first 200 people to click on the link in the description and sign up for Brilliant will get 20% off their annual subscription. And you'll be supporting SciShow Space.